consider body of water. And below the surface of water, I have a metal sheet in the shape of a square, excuse me, in the shape of a rectangle. I want to talk about the force exerted at every point on this sheet of metal due to the weight of the water. Now, I do want this sheet of metal to be parallel to the surface of the water so that the amount of force at the point on one end is going to be the same amount of force at the other end because those points are at the same depth. So let's talk about force. Force can be interpreted as mass times acceleration. And my acceleration I can refer to as the letter G. And of course, G is going to be this many meters per second squared using international units, this many feet per second squared if I'm using British units. Now, it is true that the mass can be considered the density times the volume of the body of water. Sorry, that's a V. Can you read that? My goodness. Rho times V. However, it's also the case that the volume can be interpreted as the area of the base times how deep it is. I'll call it depth. And so if I so choose, I can think of the force as being this. Product of those two constants times the depth times the area of the base. And I sometimes refer to this computation right here as the pressure. And so technically speaking, the force exerted on this particular sheet can be interpreted as pressure times area, or better yet, I can literally think of the pressure as the amount of force exerted due to unit area. But here's a relationship I want you to remember, as well as this relationship right here. Let me apply this. We will take a peek at an example of such.